Yeah, welcome everyone, and thanks for joining my talk. As Andrei said, I'm Artur Pilipenko from Azul Systems, and that's our legal slide, so I will be sharing some technical details of ongoing work at Azul, but it should not be interpreted as any product plans or commitments. So, few words on who we are. Azul Systems is a company which builds Java virtual machines. And in Java world, we are known for our scalable, low-latency implementation of the JVM. And we use LLVM at Azul Systems to build a high-performance, production-quality JIT compiler for Java. So it is a compiler which takes Java bytecode as input, produces native code, and does everything inside of a running VM. And using LLVM as a JIT for Java has certain challenges, and we and my colleagues talked about these challenges on previous developers meetings. So if you are interested, check these talks out. Specifically, we talked about interacting with precise relocating GC, and we have done a lot of work upstream to support this. We talked about interacting with runtime, with the VM, so how we do JIT, how we de-optimize, things like that. And today, I'm going to be talking about another challenge, which is expressing high-level Java-specific optimizations using LLVM. It is important for us because we are building high-tier JIT. We already have an interpreter, we have tier 1 compiler, and the ultimate goal for the compiler we make is performance of the generated code. And in order to achieve good performance, it's crucial to make use of high-level semantics of the language you compile. A good motivational example for Java is devirtualization. There are a lot of virtual invocations in Java code, but the good news is that most of these invocations are devirtualizable. So we can devirtualize, we can inline, and we can optimize through the call side boundary. But in order to devirtualize, we need to have some information in the representation we have. We need to know possible types of the receiver objects. And once we have this information, we can do much more. We can optimize type checks, we can improve aliasing, and I'm going to be talking about it later. LLVM, in turn, being originally targeted for C and C++, has rather low-level representation. And it supports the way to provide some bits of high-level information using attributes and metadata. For example, TBA, Type Based Alias Analysis, uses this. And recently it has been used as a compiler for high-level languages, so we are not the only ones who do that. We've seen Swift, JavaScript, PHP, Microsoft.NET. And it seems like a typical way to build a compiler for a high-level language using LLVM is to have some kind of high-level optimizer, probably some existing compiler, and then lower the representation of this high-level optimizer to LLVM IR to let the LLVM optimizer do the rest of transformations and the code gen. At least that's how Swift HHVM WebKit compilers are built. But if we were to write a high-level optimizer for Java, we would need to come up with some kind of high-level representation. We would need to implement analysis and transformations on it. And even though we are interested in Java-specific optimizations, they won't work alone. So we would need to implement a lot of standard transformations. And we will need some kind of infrastructure for it, path managers, things like that. That sounds like a lot of work to do. We didn't really want to do that, especially considering that LLVM already has this infrastructure. It is well tested, well maintained. So the decision was we want to make use of the existing infrastructure as much as we can. And to do this, we decided that we will express all the high-level information we need in LLVM IR, and we called the resulting IR embedded high-level IR. And we would introduce some missing Java-specific optimizations, and we also will teach some parts of the optimizer to make use of this extra information we provide. So this is the agenda for the rest of the talk, and it roughly outlines the system we built. We will talk about abstractions, which are building blocks for the high-level embedded IR. We will talk about JavaType framework, which is a mechanism to reason about object properties. And of course, we will be discussing optimizations, Java-specific and existing ones. So, as I said, abstractions are building blocks for the high-level embedded IR. They are functions with the semantics known by the optimizer. In this regard, they are very similar to LLVM intrinsics, but they have regular IR implementation. They differ from normal functions by the fact that we postpone inlining of abstractions until specific points in the pipeline. And these points, they create boundaries of optimization phases. By gradual inlining of abstractions, we also implement gradual lowering, where we start with the IR, which manipulates high-level building blocks, and we gradually simplify it by inlining their implementations. That's an example. We have an abstraction for get class ID. This function takes a Java object as an argument and returns an identifier for the class this object implements. And we can use the result of this function in a subtype check, which takes two class IDs as arguments and returns a Boolean. And as denoted by late inline attribute, these abstractions are inlined away after phases 2 and 1. So once we're done with type-specific optimizations, we can inline their bodies, and we can let the optimizer optimize the bodies itself. And that's how these abstractions are used in the real code. In Java language, there is an instance of construction which allows you to check if an object implements a particular class. And this is roughly the code we lower this construction to. So we call get class ID and then do a subtype check on the result returned by abstraction. So just having abstractions, we can do a lot of optimizations. For example, we have abstractions for acquiring and releasing locks, and using them, we can do lock coarsening and lock elision. Our GC barriers and poles are also implemented as abstractions, so we can eliminate redundant ones. Object allocation is also implemented as abstraction, and we have a special pass which does syncing of allocations down to called paths. And probably this mechanism for late inlining can be useful for others. It is rather simple and generic. It consists of an attribute to specify the inlining phase for a function, and it consists of the path itself, which does the inlining. And in your pipeline, you just schedule the path with the argument of the phase of which you want to inline away at the point you want these abstractions to be eliminated. So if the community thinks that this is a useful enhancement, we can spend some time and effort bringing this functionality upstream. So now let's talk about JavaType framework. It is a mechanism to reason about Java object properties. And specifically, we reason about their properties in terms of Java classes they may implement. In Java, hierarchy of classes is a tree. And if we have a variable of type C, we know that this variable can point to an instance of any C subclass. But in some cases, we can know that the exact type of a variable. For example, if it is a newly created object. So we represent the set of possible classes a value can implement using JavaType struct. It consists of two fields, class ID and isExact flag. An exact JavaType represents a set of a single element, which is denoted by a class ID field. A non-exact JavaType represents the set of subtypes of this class. We define several operations over JavaTypes. We have union, we have intersection, which are basically union and intersection on the types, on the sets denoted by JavaTypes. But we need to coarsen them to the nearest JavaType implementation representation. And we have an is-subtype check. We say that one JavaType is subtype of another if the set represented by one JavaType is a strict subset of another set. And we have a check if two types intersect, saying that the sets represented by these JavaTypes have elements in common. We know that it's not the best type system for Java. For example, we lose information when we do union of types. For example, if we union two unrelated class hierarchies, we need to find the least common supertype for them and represent it as a Java type of this supertype, which will include extra unnecessary classes into the set. We also know that we do not represent multiple inheritance of interfaces well, and it is supported in Java. We can represent a set of classes which implements one interface by a non-exact Java type with class ID set to this interface, but we have no way to represent a set of classes which implement several interfaces simultaneously. But it worked for us so far. And the core for the framework is the analysis, which for any given value will tell you the Java type of that value. Currently, it is implemented as value tracking style analysis, but over time it became relatively expensive. So we would like in future to do some caching of the results so we can improve the analysis without worrying about compile time. If you want to get more accurate result, you may provide the context instruction for the analysis, and it will try to give you a more accurate result for the specific context. And it can always return none. For example, if the value you passed doesn't point to a Java object, for example, if it's a derived pointer in the middle of an object or an array. And the main source of the information for Java type analysis is type information in the bytecode. Java bytecode is type annotated, and our front end emits this information to the generated IR. We attach this information to the IR using attributes and metadata. And we also made some parts of the optimizer infer this information and cache the Java types using attributes and metadata. And that's an example how it may look in the IR. As I said, it is represented using attributes on arguments and return values for both call sites and function declarations. And it is also represented as metadata on loads, indicating properties of the pointer being loaded. So when you make a Java type query, the first thing which happens, the analysis looks at the value you passed and tries to get context-insensitive result. It looks at the base facts and gets the information from attributes and metadata. If the value you pass is a fee node or a select, it will look for the types of the incoming values and will calculate the union of these types. And it also knows the semantics of some Java methods. For example, object clone will always return the object of the same type as it passed as an argument. And if you pass a context instruction, the analysis will try to do context-sensitive type sharpening, looking at the dominating conditions. So it will walk the dominator tree, which you need to pass along with the context, and it will look for type checks on the object in question. This is an example how a type check can look like. If we had get class ID and compare the result of get class ID with some constant, we know that in the context where this condition holds, we know exact Java type. We can also have a non-exact type check where we have a type off check on the result of get class ID. And in the context where this condition holds, we know non-exact Java type. So to get the final result, it will do the intersection of context-insensitive result and all the types from dominating conditions. And there can be more than one. We use metadata to represent type information, but there is a small problem here that metadata can be dropped by the optimizer, and that may inhibit further optimizations. We can go and teach various parts of the optimizer how to preserve the metadata we're interested in, but that sounds like long, tiring, and probably error-prone process, because the metadata we want to preserve is not a part of the lang ref. But on the other hand, we have Java types information which describe properties of the accessed objects. And we can use Java types to heal metadata on loads. So we have an inst combine rule for loads and stores, which looks at the memory access, gets base object being accessed, gets a Java type, and asks the VM about field layout for this object. And once we know the field layout, we know the type of the pointer being loaded, and we can also update some other metadata using the same mechanism. So now we have analysis, and now we have some type information. Let's look at the optimizations which can make use of the information we added. And let's start with Java-specific optimizations. I mentioned that devirtualization is a good motivational example, so let's take a look how we devirtualize. And in our compiler, indirect calls come in different shapes and forms. Depending on the profiling information, our front end may decide to generate one form or another. It can be either a simple explicit lookup, or we can have a profile-guided call side where we have some predicted receiver types. We have guards on the receiver type and direct calls to these expected targets. And we need to do different things in order to simplify or devirtualize these call sides. That is how explicit lookup looks like. That's a simple version of indirect call side. Resolve virtual is an abstraction here. It does lookup of the target method, and then we have an indirect call on the result of it. And in order to devirtualize this call side, we need to do constant folding of resolve abstractions for known receiver types. So we have a pass which does it, looks for resolve calls, checks their Java types, and asks the VM if the VM knows the devirtualized target for such calls. Profile-guided call sides are a little bit different. As I said, we have type checks and guards, and we have static calls to the expected targets. In this example, we have one predicted receiver type, we have one type check and one static call, and if this guard fails, we just de-optimize. So in order to simplify this call side, we need to fold the comparison. This way we can fold the control flow and end up with either a static call to the expected target or with de-optimize in rare case. And profile-guided call sides can be even more complicated. Here we have 3 expected receiver types and 3 targets. The guard is implemented as a switch, and as a fallback, we use explicit lookup. So to simplify this call side, we need to prune impossible case switches, and probably we need to fold resolve abstraction. So in order to simplify the control flow we get from profile-guided call sides, we have several inst combine optimizations. So let's look at the guard we will usually have for a type check. If we know the Java type for the object, we know the set of classes this object can implement. And if we know that if we know the exact Java type, we know that it can only implement one class, so we can fold get class ID to a constant in this case. If we cannot fold it to a constant, we can check if the sum class we're comparing with belongs to this set of classes object can implement. And if it is not, if these types do not intersect, we know that the comparison can never be true. So it can be optimized to false. And we apply the same idea to optimize, to prune switch cases, but it is not an inst combine rule, but a separate pass because it manipulates control flow. This is another optimization we can do when we have type information in the IR. This is a code sequence we normally generate for instance of construction in Java code. And again, if we know Java type for the object, we know the set of classes this object can implement. And for example, if we know that the set of classes object can implement is a strict subset of parent subtypes, so it is subtype of parent type, we know that the comparison is always true, so we can fold it to true. And vice versa, if we know that these sets cannot intersect, we can optimize the comparison to false. Another small optimization for this sequence, if we know that parent does not have subtypes, we can replace this abstraction call with explicit comparison with constant. So now let's look how existing optimizations can make use of the information we added. Let's start with alias analysis. LLVM already has a mechanism for type-based alias analysis. In order to use it, you need to represent the type system in DAG, and you need to attach metadata describing type properties of memory access to your memory access instructions. We use this mechanism for Java code. It works fairly well, but it is not ideal. The problem with TBAA is that it has not changed as the code is transformed. Well, it has dropped like any other metadata, but it's not what I mean here. Often when we optimize, we can refine types, for example, after inlining or some control flow simplification, but it does not refine TBAA tags. On the other hand, we have JavaType framework, which maintains the same information. And it benefits from more sophisticated analysis. It benefits from metadata healing. And the types are refined as we transform the code. So we decided to introduce JavaType based analysis for our optimizer. And the rule here is simple. We have 2 pointers. We look at their base objects being accessed. And if Java types do not intersect for these objects, we know that pointers cannot alias. As I mentioned, we wanted to make use of context-sensitive type sharpening for alias analysis, but it was a little bit tricky because of the way how LLVM alias analysis is organized today. When an aliasing query is made, there is no context instruction. We have a set of metadata which describes aliasing properties of the instruction, but we don't have the instruction itself, so we have nothing to pass to JavaType analysis. So we had to hack around it a little bit. To do this, we cached the result of JavaType query for base object being accessed in metadata on loads and stores. We introduced new metadata, and we created an instCombine rule which maintains this metadata. So here is an example. We have some object, we have type check on this object, and we have a load in the context where we know exact type for this object. And since we know context-sensitive type here, instCombine attaches corresponding metadata, and this metadata is taken into account when we are making aliasing queries. Another information which we can gather from Java types is dereferenceability. LLVM uses dereferenceability information to check if it's safe to speculate a load. And normally this information is expressed using dereferenceable and dereferenceable or null attributes and metadata. At the same time, when we know Java types, we know the layout of the object, and we know exactly how many bytes are dereferenceable from a pointer. And Java type information is going to be more accurate because it benefits from more sophisticated analysis. For example, in Java types, we handle control flow merges, and currently the dereferenceability analysis in LLVM doesn't. And it also benefits from type sharpening. So that's another extension we made to our optimizer. I mentioned several optimizations which together can significantly affect the shape of the code. So we wanted LLVM Inliner to take these optimizations into account while making inlining decisions. To do that, we taught Inline Cost about JavaType based optimizations. Inline Cost looks at the call side and the body of the callee, and it estimates the effect of potential optimizations if the callee is inlined at this call side. So we made instCombine maintain Java types on arguments of call sides. We attach this information using attributes for arguments, and we made Inline Cost use the information from argument types to estimate the effect of potential optimizations. Here's a couple of examples which can significantly affect the inline cost. As I said, we can have profile-guided call sites where we have a type check and a static call to the expected target. We can inline this expected target, and we can have type checks and the inlined bodies of these targets. And when we consider this code for inlining into its caller, we can know that one of these type checks can be optimized away. So we know that one of the inline targets will disappear. And we don't need to take this part of the method into account while calculating inline cost. And on the same note, if we have a virtual call with explicit lookup, and we know that after inlining we can devirtualize this call, we will give a generous bonus for inlining. So we encourage inlining, which leads to devirtualization, and it will probably lead to further inlining. The system I have described, we've built incrementally over the course of last 2 years, and of course there are things we would like to improve. We would like to make JavaType analysis a fully fledged analysis pass. This way we can cache the results and we can improve our analysis without worrying about compile time much. It will be nice to improve our type system. It will be nice to be able to represent multiple inheritance of interfaces or some array type information. For example, we can have array length as a part of type system, and we can do some optimizations about it. And like with everything else we built, we would be happy to see this upstream and being used by others. Well, granted, the JavaType framework is Java specific, but we think that this framework can be generalized. So if you are working in a language which will require similar functionality, welcome and talk to us. Probably we need to discuss and to think about the shape for a generalized type framework which will make sense upstream. So to summarize, we created an optimizer for Java based on LLVM. We expressed Java-specific semantics using high-level embedded IR, and it turned out to be really flexible and low-cost representation. We introduced several Java-specific optimizations, but other than that, we heavily rely on the existing optimizations and infrastructure. And we also made some existing optimizations benefit from the information we added. Thank you for your attention, and I will answer your questions now.
Yeah, thank you, Artur. You are sharp on time. So questions, I guess I'm supposed to run to anyone who wants to ask. So guys, raise your hands. Okay, you will be the second.
Hey, hello. I really enjoyed the talk, so thank you. What? Okay, closure. Yeah. But you actually mentioned some GC optimizations that were also possible, like in one slide.
Yep.
So could you please go into a little bit of detail as to what kind of garbage collection optimizations were enabled because of all of this?
For example, we have an abstraction to represent a GC poll. We need to have GC polls in the code we generate. And we have some kind of heuristic how to insert this, how to have these polls in the code. For example, we have a GC poll at the entry of a function. And for example, after inlining, we can end up with extra entry polls from inlined methods. So we have an optimizations to eliminate these GC polls.
Thanks.
So, second question from a back row.
Hi. I was just wondering how much you found the Java-specific optimizations and the LLVM optimizations interacted. Like, is it mostly you do the Java ones and then the LLVM standard passes, or are they interleaved quite a bit?
In our pipeline, they interleaved and they actually interact a lot. For example, as I said, devirtualization, and in order to devirtualize, we need to find out Java types, and to find out Java types, we need to, for example, simplify control flow of a method, and in order to do that, we need to do some constant folding. It's all very interleaved.
All right, more questions? Yeah, I'm coming.
Hi. Just a follow-up question to that one. You're doing several stages of inlining and interleaved LLVM and your own optimizations. Do you have any? Did you have any findings on how the several stages of inlining affect your performance?
Well, actually, when I said that we have several stages of inlining, that was about inlining of abstractions. So it is not inlining of application code. It is inlining of this these helpers.
Okay.
Well, in fact, we do run inliner in some kind of iteration, and there is some interaction between the virtualization, which can open inlining opportunities, and inlining, which can provide more context. So we have some kind of iteration here.
Okay, thank you.
Who is next? Right. So thank you, Artur, for a great talk.
Thank you.